Okay, there we go. So welcome. I think this is the last section of AMAT 350. So numerical differential equations. So as we have mentioned, we'll be exploring some numerical techniques on how to solve differential equations, be it ordinary or partial differential equations. Now, I am treating this as a specialty course. There is no definite outline to it. So kaya medyo free tayo to explore different topics. Of course, I cannot forgo the classical ones, pero hindi ko i-discuss lahat ng classicals. So maybe I'll just give you an in-depth analysis of one method. Halimbawa, Eulers Method, titingnan natin yung derivation ng method, yung implementation ng method, and a little bit of error and convergence analysis of the method. And then as we go along, I'll introduce some generalizations of Euler's method. Tapos titingnan na lang natin yung derivation niya, a little bit on the error analysis, a little bit on the convergence analysis, but not heavy on the theory, more on the implementation and the method itself. Now, this is designed not to teach you everything, but this is designed to teach you how to study, or how to look at a particular method. Because pag nagre-research na kayo, ang research kasi hindi siya textbook problem no? Kayo yung pipili ng method and you should not be limited with the methods that you learn in classes. So really, this is really an experience, a teaching experience, not just the methods itself, but how you do or how you study the methods, or how do you look for methods and how to improve methods. Kasi baka meron kayong nakitang isang method, tapos gusto niyo siyang i-improve. Makita nyo kung ano yung analysis na kailangan nyo gawin o ano yung mga posibleng options para ma-improve nyo yung isang particular technique. Okay? So the objectives for this first module that I shared with you is to first use Euler's method to solve an ordinary differential equation, do an error and convergence analysis of Euler's method, and use Euler's method to solve scientific problems. Let's see if we can go with number 3. Pero definitely number 1 and number 2 will be done. And natapos yung pagpapanggap ng module, handwritten na yung natira. Wala akong time mag-latex. But essentially, section A is just describing what ordinary differential equations are. But I think based on the Google form, you already know, or you already encountered ordinary differential equations. So I don't need to dwell much on section A. The main takeaway here is that ordinary differential equations are just equations involving the derivative of a function of a single variable. Okay? Or it could be a function of several variables, but you are just differentiating with respect to one of its variables. So pag meron kang equation, a first order differential equation, most likely you can write it in the form 10.1. And this is what I'll refer to as the standard form. So sa ating klase, when talking about ODEs, ito yung gusto ko laging forma. Kasi I'll try to write I'll try to derive the methods that are apt for implementation for ODEs that are in the form of equation 10.1. So here we have the independent variable x, the dependent variable x which depends on the variable t. Variable t kasi piniprepare ko to sa interpretation na we are differentiating with respect to time, and then x is this is a function value which represents space. So really it's still the spatial and the temporal aspects of a problem. Pero here we are just concerned with changes with respect to time. Of course, it's just a play on the variables. If you drop the interpretation that t is time and x is space, everything will still work. Even if x is your time and t is the space and whatnot, so mag-work pa rin siya. Pero yeah, yung makikita nyo i-derive natin mga methods ay nasa forma ng equation 10.1. So we're looking for the function x of the independent variable t whose derivative is equal to the function f, right? But f is not an explicit function in terms of the independent variable t because the function f on the right-hand side might still involve the dependent variable. So basically, you can think of it as another function acting on both the independent and the dependent variable. So para mas generic, hindi kailangan explicit yung form, meaning lahat ng x's or lahat ng independent variables ay nasa right-hand side. So we're taking the possibility, or we're considering the possibility that the right-hand side involves the dependent variable. So yun nga lang, ang gusto ko yung derivative ay nandun sa left-hand side. So basically, this poses the question of finding the function x whose derivative with respect to time in implicit form is equal to the function f of both the independent and the dependent variable. And this is one distinguishing characteristic of differential equations to your usual familiar equations in one dimension. Kasi rito, hindi lang tayo naghahanap ng set of numbers or set of objects that satisfy the differential the equation. Here we're looking for a function. At ito yung mahirap ipa-appreciate sa mga estudyante, ano, kasi lagi pa rin nila i-conclude mag-Euler method kami. Ang ibibigay niya lang sa aking solution ay yung final number na makikita niya sa iteration ng Euler method, which is wrong because essentially what we're trying to approximate here is a function x. So a number, a single value, will not work as an estimate for the solution. I'm looking for a bunch of function values over the discretization mesh. All right? So differential equation, standard forms equation 10.1, maghahanap tayo ng function. But of course, at the back of our minds, we are developing numerical methods. So ang hinahanap ko ngayon ay mag-i-involve ng discretization. So I will be looking for a bunch of function values that will approximate the function values of under the function x at various specific values of the independent variable t. Okay, so I think if you want to review ODEs, you can go through examples 10.1, I think 10.2, kasi rito, diniscuss ko lang naman paano nga nagsasolve ng ODE. For instance, 10.2 is already in standard form, and this is a separable differential equation. You can simply multiply both sides by x dt and then integrate, then makukuha mo yung solution, the exact solution. And I just included this here to tell my students, tingnan nyo, ang solution yung hinahanap ay isang function. Actually, in this case, dalawang functions yung kanyang solution. At hindi lamang isang number yung hinahanap natin. Right? And the motivation behind the ODEs ay medyo kakaiba. Kasi hindi lahat ng ODEs ay kaya nating isolve by hand. Even if we are sure that an ODE is solvable, hindi natin usually kayang isolve sila by hand. If you already taught ODEs in the undergraduate level, matatandaan nyo na ang daming mga methods para mag-solve ng ODEs. Pero yung mga methods na yun ay nakadepende kung ano yung itsura ng ODEs. Ano yung mga component functions sa mga ODEs. Some could be separable, that's fine. Some could be exact. So meron tayong algorithm by hand kung paano isa-solve ang isang exact differential equation. And then there's a different solution if your differential equation has components that are homogeneous of a certain degree. Pwede ka rin mag-variation of parameters, reduction of order, method of undetermined coefficient for general linear differential equations. So there's a lot of methods, pero yung mga methods na yun, posibleng hindi mag-work sa isang ODE. And hence, really, the appetite for developing nice numerical algorithms that can circumvent all those problems sa pagsosolve by hand. Kasi unang problem nga ron, aling method ang mag-a-apply. And usually, you won't see which method is applicable before doing heavy calculations. Ano? So a priori, walang method or hindi madaling makita kung kailan mag-a-apply ang isang particular method para sa isang ODE na solution by hand. So that's why mas okay or mas gusto ng karamihan, especially the applied scientists, to really work with numerical methods para sa mga ODEs. Okay? Now, I'll skip this. Equation 10.2, ano lang naman to? I think this is a linear first-order differential equation that can easily be solved by introducing an integrating factor kasi simple yung function na nakakibat kay x. So, ang integrating factor niya lang ay ito. So, if you've already forgot that and you want to review, so revisit example 10.2. And here's where I want to begin formally. Now, I guess the simplest method para sa pag-solve ng isang ordinary differential equation ay yung tinatawag natin na Eulers Method. Okay? So this is a very simple technique sa pag-solve ng isang first-order ODE with an initial condition. So we considered the system given by equations 10.7 and 10.8. So you see in 10.7 our standard form. Pero in-instantiate ko na to sa isang closed interval AB. So T belongs to the closed interval AB. And then we're given an initial condition para makuha natin yung unique solution. Because probably that's one drawback and perhaps an acceptable one of numerical methods. Kasi dito, numbers lang yung ibibigay sa atin. So definitely, we're looking for unique solutions or we're looking for optimal or efficient solutions or the best or the desired solutions to an ODE. Kasi kung maalala nyo, ang mga ODEs, pag wala ka dyan binigay na initial condition, there could be infinitely many solutions, right? Kaya may mga parameters dun sa solution. Pero once you give enough initial conditions, and if your problem is well posed, then you're going to get a unique solution. And we're after looking for solutions or approximations to the solutions to ODEs na mayroong exact symbolic solution. Okay? So ito yung itatry natin i-solve. System 10.7 to 10.8, the initial condition is that x of alpha, or the function value at the left endpoint, x of a, so which is the function value at the left endpoint is equal to the number alpha. Of course, we cannot just plug this into our computers because computers are finite by nature. So kailangan kong hatiin yung data. Hindi siya mag-admit ng continuous data, so I need to discretize it. So I need to chop it off into a number of into a finite number of data points, right? So kaya gagawin ko, instead of considering the closed interval AB for t, kasi dito ko gustong i-solve yung ODE, pero dahil nga hindi to tatanggapin ni computer yung closed interval AB, ang gagawin ko, hatiin ko yung closed interval AB into various points, a finite number of points. I will let A to be equal to T sub 0, and then B to be my T sub capital N. So I'll have a total of capital N plus 1 points ranging from the interval AB. Tapos dito ako magfo-focus. So we'll call this our discretized mesh or our discretized domain. So meron tayong n plus 1 data points. And the idea is, hindi na tayo ngayon naghahanap ng isang function. Sa traditional ODE approach by hand, ang hinahanap natin ay isang function na nakakasatisfy ng differential equation plus the initial condition. But in the machine implementation of the solution to this ODE, we'll be looking for a bunch of numbers. And what do those numbers represent? They represent the function values of the solution X dito sa mga discretization points. All right? So yung interval AB, hatiin ko sa n plus 1 points. At ang goal ko ngayon ay makahanap ng approximate sa function value under the function X ng bawat discretization point na yon. And hence, instead of a function X, a continuous function X as my solution, I'm looking for a vector or a collection of finite W sub i's that will approximate X sub T sub I. And for brevity of notations, I will denote X of T sub I by X sub I. So yung mga W sub I, sila yung mga numbers na magagaling sa ating computers, which will be our estimate para dun sa mga function values. And if you really want to get a picture of how your solution compared to the true solution or to the continuous solution, magi-interpolate lang tayo. Interpolate natin or kukunin natin yung best fit dun sa mga W sub i's natin, and that will be our estimate for the function X. Pero in reality, what our computers will output will just be a vector of numbers, a vector of estimates to the function values under X of our discretization points T sub 0 until T sub n. Okay? So clear ba yung general structure na yun? So yun yung mangyayari. I hope that's clear. Kasi ito yung nagkakaproblema ako sa mga undergrad. Hindi nila nag-grasp na ang W sub i's, hindi yung huling W sub I yung titingnan ko. Kasi lagi lang nilang binibigay, or karamihan sa kanila, lalo na sa simula, ang binibigay lang sa akin nila sa akin na solution ay W sub capital N, which is the last number that they say, and they fail to recognize that we are after actually a continuous function at first. Pero dahil nga hindi kaya ng computers to work with continuous data, ang ginagawa natin, dinidiscretize. So ang solution dito ay isang solution vector, W sub 0 until W sub n. Bawat isa sa kanila ay estimate para sa x of t sub 0 hanggang x of t sub n. Okay? So that's our goal. Now, how do we do this? Well, the classical approach is to replace the derivative in the derivative in equation 10.7 by a finite difference. Because remember, the definition of this derivative, this is just the limit of x of t sub I plus 1 minus x of t all over t sub I plus 1 minus t sub I as t sub I approaches t sub I plus 1, or the other way around, right? Ito lang yung definition ng derivative. Now, since there's a limiting procedure there, it becomes a continuous problem. And again, computers cannot handle continuous computations. Kaya ang gagawin ko, itong derivative na to, papalitan ko by something that a computer can compute, which is basically just a divided difference. So itong derivative na to, papalitan ko lang by an approximation. And as I've mentioned, this is just x of t sub I plus 1 minus x of t sub I all over t sub I plus 1 minus t sub I. I'll drop the limit because, again, computers cannot handle continuous operations. Kaya nangyari, ito yung nakukuha nating approximate. But instead of x of t sub I, pinalitan ko na siya ng w sub I. Kasi yan yung gusto natin sa formula natin. Kasi ang kinukuha natin ay mga estimates na w sub I. They are not exactly x of t sub I. But if the w sub I are all good estimates to our x of t sub I, and h sub I is close enough to 0, then we get a good, this becomes a good approximation to the instantaneous rate of change or to the derivative. Kaya usually ginagawa ko or ginagawa sa classical methods, nagtatry muna na palitan yung derivative by a divided difference. And that will cause a shift on the right-hand side. The original right-hand side is f of t of x, but that represents the actual derivative. Now, once you discretize, so to speak, the derivative, mababago yung right-hand side. Hindi na lang siya basta f, right? Because you'll need to follow some rules with respect to taking the expansion of x or the representation of x as a finite difference. So this will be altered a little bit. Instead of a right-hand side that will be just the function f given in our standard form, mapapalitan siya ng isang function or isang expression phi which involves f, the t sub I, the w sub I, possibly w sub I plus 1, and h sub I. Here I am writing h sub I for t sub I plus 1 minus t sub I. Siya lang yung increment dun sa discretization dun sa x-axis, right? So h sub I is the difference between two consecutive t sub I's. Usually we choose h sub I to be constant, all right, or to be equal to each other. So meron tayong uniform step size. Pero in general, h sub I can vary. Okay. Now, kapag meron tayong isang method, kasi rito sa method na to, all you need to do to find w sub I plus 1 ay mag-multiply ka lang ng h sub I both sides, tapos lahat ng may w sub I ilagay mo sa left side, lahat ng may w sub I lamang ilipat mo sa right side, then you'll get an expression for w sub I plus 1. So once you have written equation 10.7 into the form 10.9 via an approximative way, right? So makakakuha ka ng isa ng method para sa pagsosolve ng ODE. Now, any method born out of equation 10.9 is called a one-step method. It's a one-step method because we're just moving forward in time or in the independent variable one step at a time. Kasi rito, ang involved lamang possibly in this equation is t sub I plus 1, and their function values. So basically, in solving for w sub I plus 1, all we need would be w sub I and the t sub i's possibly. All right? Kaya siya one step. Kasi kailangan mo lang yung value ngayon para ma-predict yung susunod na value. Pag nandun ka na sa susunod na value, isa lang previous function value yung gagamitin mo to get to the next one. All right? Kaya siya one-step method yung tawag. Tapos kapag ina-arrange natin to in such a way that w sub I plus 1 is computed in terms of the w sub i's, we call it a time marching algorithm or a forward marching algorithm. Kasi pa-forward yung takbo mo. Magsisimula ka sa W sub 0 all the way to W sub 1 and then W sub 2, W sub 3 until W sub n. Okay, kaya siya time varying. Well, and this is usually the case since we have an initial condition. Dito tayo lagi usually nag-start dun sa initial condition. This is our input data to our numerical method. Dito tayo nagsisimula. And then kung meron kang isang one-step method, yung value dito, which is exactly alpha given in the problem, we will set this to be our W sub 0, our initial condition. And then if we have a one-step forward algorithm, then W sub 0 will lead us into finding W sub 1. And then we know W sub 1 will give us W sub 2, and so on. Kaya siya marching algorithm at one step. Okay. Now, there's another thing here, just to finish all of those definitions. When the right-hand side, after simplification, if you can write W sub I plus 1 equals an expression that doesn't involve W sub I plus 1, then we call that an explicit method. Explicit siya kapag ka walang W sub I dun sa right-hand side. Meaning, you can compute W sub I plus 1 using only W sub I, H sub I, F, T sub I, W sub I, H sub I. Walang W sub I plus 1 dun sa kanan. Okay. Now, that is easier because if we cannot really isolate the W sub I from one side to the other, magmamroblema na tayo doon. Magkakaroon tayo ng isang nonlinear equation. And solving nonlinear equations is another monster of its own. Ano? So isa uling section sa Math 175 yung pagko-compute ng solutions or approximations sa solution ng isang nonlinear equation. Pero that would have been very helpful, especially if we have an implicit method. Kapag ka hindi natin ma-isolate si W sub I plus 1 sa isang side ng equation 10.9. But Euler's method, luckily, is a one-step time-marching algorithm that is explicit, meaning we can solve for W sub I plus 1 explicitly in terms of the previous data, the previously available data. Okay. Now, let's take a look at the derivation of Euler's method itself. Now, this is hinged upon a very familiar result na parang nung math, nung elementary calculus natin, parang we just gloss over that. Ginagawa lang natin siya kasi nasa exercise and so on. But this is really very helpful, especially for these applications. The Taylor series expansion. Okay. So we'll just look for the Taylor series expansion of the function x around the number t sub I. Okay, and that's what is given in equation 10.9. In-expand ko lang or kinuha ko yung Taylor series expansion ni x, pero pinutol ko hanggang dun lang sa second order term. Okay, that's why I have a number c here, because really, kung ayaw niyo yung putulin, t sub I pa rin yung nandito, plus you'll have what? You'll have t minus t sub I cubed all over h cubed, x triple prime of t sub I, and so on. All right. But once you cut, actually hindi lang Taylor series expansion to, pati Taylor remainder theorem. Once you cut it on a certain order of the derivative, in this particular case, I cut the expansion down to the second order, right? Pwede mo pa rin ma-maintain yung equality by just because ano nga ba yung ginamit dito? Mean value theorem. Gumamit ka ng mean value theorem to prove the existence of a number c such that all of the remaining terms in the infinite series ay equal lamang dito. So 1/2 t minus t sub I squared x double prime at the number c, where c is a number between t and t sub I. So I hope you will not be complaining na, sir, bakit to equal? Finite lamang yung expression mo dyan. Yeah, that's right. Pero sinabi ko na si c ay isang unknown number between t and t sub I. And by the mean value theorem, I know that that number exists, so that this term here represents the entirety of the truncated terms. So isa siyang sort of truncated series expansion, truncated Taylor series expansion, but I take note of the remainder term. I take note of the remainder term para keep track ko kung ano yung error. Para magkaroon ako ng idea gaano kaganda yung estimate na nakukuha ko. Right? If you're thinking this is too cheap an approximation to x of t, then wait for the next meeting or the next module kasi dun sa susunod na module, hahabaan ko yung expansion. Alright? Pero ngayon sa Eulers method, hanggang second derivative lang talaga yung kinukuha niya sa expansion. And actually, the second derivative will serve as the error term. Okay? Now, I'll just shift the notations here, right? So from equation 10.9, so sorry, that's equation 10.9 tayo. If we go back to the problem, equation 10.7, sa equation 10.7, meron tayo nito. The derivative the derivative of x with respect to t is equal to f of t comma x. So meaning, kung matatandaan nyo dun sa Taylor series expansion, kailangan natin yung kailangan ko yung x prime of t sub I, right? I need x prime of t sub I, which is basically x prime of I from our shorthand notation. But from this equation, x sub I prime is actually equal to f of t sub I comma x sub I. All right? So yung expressions na x sub I prime doon sa Taylor series expansion, pwede kong palitan ng f of t sub I x sub I. And that's the beauty of having your differential equation in standard form. Kasi yung derivative dun sa Taylor series expansion, pwede mong palitan ng function value under the function little f. All right? And that's what I did to get equation 10.10. Okay? So it's an ano nga bang ginawa ko rito? I plug in t sub I. Let me see. Yeah, I plug in t equals t sub I. So kaya ito ay naging x of t sub I. So by our shorthand notation, that's x sub I plus 1. Tapos si x sub I, copied over lang siya. Kasi ito ay x of t sub I dun sa Taylor series expansion. Shorthand notation. And then if I plug in t equals t sub I plus 1, so this would be t sub I plus 1 minus t sub I, we'll get h sub I. And then this is x sub I prime. By the analysis that we did in equation 10.7, it can be written as f of x sub I t sub I. And then the rest will follow accordingly, right? Madali lang pala to kasi hindi ko napapalitan yung x double prime of c. Why? Because c is not is an unknown number. We don't know what the number is except that it is a number between t sub I plus 1 and t sub I. We don't know if c is one of the discretization points. Actually, hindi pala siya discretization point kasi siya ay isang number lang sa pagitan ni t sub I plus 1 at ni t sub I. But we don't care about this because this is just the error term, and in reality, we don't have access to the exact error. Ano? Kasi kung alam mo yung eksaktong error, edi alam mo na kung ano yung eksaktong value. And kasi i-add mo lang siya dun sa estimate. So that's impossible to, it's impossible to get our hand practically and theoretically on x double prime of c. So we'll just keep it there, okay? And I'll drop this for a moment to get my estimates. So kaya ang pwede kong gawin pala, si x sub I plus 1 ay approximately equal dito plus this guy. Tapos tatanggalin ko to kasi wala akong access dyan. And I'm just hoping that this term is very, very small or something close to 0. And hence we get the Taylor's method. Taylor's method tells us that w sub I plus 1, kasi nga si x sub I plus 1 ina-approximate natin by w sub I plus 1. And then we don't know the exact x sub I. Yun sana yung gagamitin ko sa equation 10.10. But we don't know what x sub I is. So papalitan ko lang siya ng w sub I. H sub I will go there. And then can we compute f of x sub I comma t sub I? Nagulo yung arrangement ko ng variables. Pero dapat ito ay Hindi ko siya ma-edit, pero dapat ito ay T sub I, gamma W sub I. Though, anticipate nyo na to, hindi ako naging particular dun sa ordering ng arguments ni F. Basta meron kayong T sub I na nakita, yun yung independent variable. If you see a W or an X, that's the dependent variable. Alright? So, minsan napapagpalit ko kasi kung sino yung inuuna ko. Minsan inuuna ko si T, minsan inuuna ko si X, or minsan inuuna ko si W. Pero our understanding, T is the independent variable, W and X represents the dependent variable. Okay? Now, my question was, can we compute this? Well, of course, because the function f is explicitly given in the problem. And so this is allowed, except that we don't know what x sub I is. Pero dahil we are saying that x sub I will be approximated by the w sub i's, so whenever we want x sub I, we can replace it by w sub I. And it is now evident that this is a one-step method, explicit method. So one step siya kasi to get w sub I plus 1, we're just using values with the index I. So previous values lang yung ginagamit natin. It's a forward marching algorithm because basically we're starting with w sub I and then we're getting w sub I plus 1. It's explicit because here w sub I plus 1 is computed explicitly in terms of previously known values. Wala nang w sub I dito, walang w sub I plus 1 dito sa kanan. Okay? But of course, you need a starting point. Kasi, yes, Ben Paul?
Sir, yung sa annotation niya lang, talaga bang W sub I yung nasa right or X sub I?
Sa 10.11?
10.10, sir.
Sa 10.10. Yeah. Dapat ito ay X sub I pa muna. Thank you. Kasi theoretical ano pa lang siya, no? Theoretical derivation pa lang. Kasi sa equation 10.7, ina-assume ko pa na alam ko yung data. So, nagkaroon ka na dun ng discretization error, tapos we will compound it a little bit because we don't know all of the x sub i's. Pero meron tayong isang alam na eksaktong x sub I. Alam ko yung x sub 0. Kasi dun sa problem, given yung x of A, which is x of t sub 0, by our shorthand notation, that's x sub 0, and this is equal to alpha. And that would be our starting condition. And then siya ay eksaktong x sub 0, but what we get out of this is an approximation for, or when I plug this into here, pwede ko siyang magamit dito, w sub 0, pero makukuha ko na estimate para kay x sub 1. So para lang consistent yung notation sa Euler method, which is given by 10.11, okay? So ginawa ko na lang tong w sub 0, but this is exactly x sub 0. Pero you feed whatever the previous value of w you have. So if you feed mo lang yung value ni w sub I into this formula, you're gonna get w sub I plus 1. At ito na yung tinatawag natin na Euler's method. Simpleng-simple ng method, ano? So siguro you might be thinking that naunahan lang tayo ni Euler. Pero naunahan niya tayo thousands of years. Ano? So yeah, that's Euler's method. Now, just to see as an exercise, let's try to implement Euler's method. Now, I have equation 10.4 here. So what you can do is, if you want to practice your programming, you can try to recreate the examples I have in the module. All right. You can use MATLAB, you can use Python, or whatever programming language you're familiar with or you're comfortable with. Pwede ngang Excel dito kasi ang dali nito, no? So isang higit lang to kay Excel, sa formula sa Excel, makukuha mo na yung mga W sub i's. So let's just picture it out and look at tangible evidence of how Euler's method works. So halimbawa, equation 10.4. So ang equation natin ay dx over dt equals tx na equals t over x, where t belongs to the closed interval 0 to 5. And our initial condition is that x of 0 ay equal kay 1. Tapos you need to decide, ano ba yung mga degrees of freedom natin dito? Oh, by the way, here in equation 10.11, I just assumed that I'm using different step sizes just to make the error analysis easier. Because actually, kapag ka naman free ka na gumamit ng data, or if you have access to the formula for the function little f, then you can use any step size that you want. Okay? So pwede kang pumili, just for simplicity, equally spaced na lamang yung mga t-subies natin. But kung halimbawa limited lamang yung data mo, so specific lang yung mga t-subies na may access ka, so pwedeng iba-iba yung mga h-subai. So there could have been an h-subai in equation 10.11. Pero here, I guess I assume that I'm using the same step size, or just for para lang matama yung module, dapat ito ay h-sabay. Kasi kinary over ko pa lang pala siya doon. Right? So kindly make those annotations dun sa module. There's a lot of typos sprinkled all over the module. So we'll discover them as we go along. So I hope you're taking notes kung saan yung dapat yung i-correct. Pero yeah, there should be an h-sabay there, but in practice, we're choosing h to be uniform, or the h-subies to be uniform. Okay. Like in example 10.4, I said here that you need to use step size h equals 0.5. Okay. So medyo ano to, medyo maliit pa yung step size. Medyo malaki pa yung step size, because usually you want h to be very small. And we'll see later why exactly we want h to be very, very small. Now, okay, so if you are paying attention to example, I think it's example 10.1, sinolve ko to by hand. Madali lang naman siya kasi separable naman yung differential equation by just multiplying both sides of this guy by x dt. Then you can integrate, then you'll get the exact solution. All right. Then you plug in the initial condition to get the particular solution. Okay. Pero gamitin natin Euler's method. Now, if we'll be using Euler's method, then the pseudocode, or actually the framework, will look like equation 10.13. Remember, you have your starting condition that's given in the problem. Okay, there was ayon. Okay, and then you just copy equation 10.11. So you got this guy, convert it using the information from our problem. So w sub I plus 1 is on the left-hand side. W sub I is still there. Hindi natin siya papalitan. H sub I, we're using uniform step sizes. So all of the H sub I's are equal to 0.5. And then f of t sub I comma W sub I. Remember, in standard form, the right-hand side of your equation is your f of t x. So ibig sabihin, kailangan ko lang i-evaluate itong function na to at the discretization points and their function values. So I should have a t over x in my Euler formula evaluated at time t sub I. So kaakibat ng pag-evaluate sa time t sub I, yung pagkuha ng estimate kay x sub I using w sub I. Okay? And if you look at 10.13, it's not that hard to implement, right? Kasi ano lang siya, isang higit nga lang to kay Excel, no? You know w sub 0. Then you compute for w sub, actually may sub pan typo. This should be from 0 to 10. Tama yan, 0 to 10. So, 0 to, yeah, I think 0 to 10 or 0 to 9. Tingnan natin later. 0, 0, yeah. But essentially, dun sa code, mafi-figure out nyo kung saan ka dapat matatapos. But essentially, when you know w sub 0, you just plug in I equals 0 here, 0, 0, 0, 0. So you'll have w sub 1 on the left side, plug w sub 1 in. T sub I is your discretization point. So remember, our t's or t sub I start from 0, 0.5, 1, 1.5, all the way up to 5. All right. Kasi nga ang step size natin ay 0.5. We start with A. We grow by increment 0.5. So ito yung mga t sub I's natin. So you have access to all of the t sub I's all at once. Pero pa isa-isa lamang yung nakukuha natin na w sub I's. But w sub 0 is already given, so I can plug that in there to get w sub 1. So pwede nga natin itong manu-manuhin, no? So we'll get 1 here, and then we'll get 0.5 here. We'll get another 1 here. So we'll get 1.25. And andun siya. Or bakit 1? Mali yung compute ko. Ito ay 1. Ito ay 0.5. So it's going to be 0.5, 0.25, 1 plus 0.25. Bakit may sobra dun sa aking ano? May sobra dun sa aking tama bang computation ko? Bakit mali yung table ko? Lahat pala hindi ko na pinansin, no? Kapag kasi, sorry, nakita ko na. Ang T sub, hindi, tama ba? T sub I. Yeah, T sub 0 pala yung kailangan ko rito. Right? So this is W sub 0 plus 0.5 times T sub 0 over W sub 0. So this would be 1, then this would be 0 kasi T sub 0 yung kailangan ko. Tapos W sub 0 is 1. So that's going to be 1 plus 0 over 1 times 0.5. So that's going to be 1. So tama yung program ko. Mali yung computation ko by hand. Okay? So and then, actually kaya nga siyang manu-manuhin eh. No? Once you get W sub 1, you will be able to get W sub 2 using the forward formula. Okay? And then you can generate the rest of the table. When I ask you what's your approximate solution, you will not just tell me 5.036038 because that's our estimate for x sub 10 or the function value at the function value of the function x at the number t sub 11, which is 0.5, right? So estimate lang siya sa function value dun sa kanan. So the totality or the set of this function values would be my estimate to the function x. And just to gauge the accuracy of the method, kasi alam ko yung true solution, nag-add ako dito ng isang column, these are the true numbers or the true values that we're trying to estimate. Okay? And then to make the analysis complete, naglagay pa ako ng isang column for the relative error. Well, the relative error is the percentage error. So this is basically the absolute value of W sub I minus X sub I. So this is what we call the absolute error. Kasi siya yung difference lang ng estimate and the true value divided by the absolute value of the true value. Para this guy can be interpreted as, say, a 10% error. This is an 11% error. This is an 8.47% error. Kasi nga, relative error na siya. Laging mas okay na mag-describe ng error using the relative error so that you know with respect to what value the error is. Baka naman 1 nga yung error pero 100 naman yung ina-approximate niya. Kesa dun sa 0.1 yung error tapos 0.2 yung ina-approximate niya. So mas okay na laging relative error yung titingnan. Okay? And just so these are the local measure of errors. Local in the sense that we're looking at what are the errors at each of the t sub i's. Okay, so what's the difference between the estimated function value and the true function value? Now, if you want to get a global idea of the error, you can either compute the average relative error. So just giving equal weights to all of these. So kunin mo yung average ng relative error. So we can say that our approximation is around 4.62% yung error niya. So it's a little bit good for most applications. Kasi sa engineering, okay sa kanila yung 5 to 10% error. They're happy with it. Pero sa math, di ba, tayo ay malungkot tayo kapag ang error ay 10 to the minus 3. Gusto natin 10 to the minus 6. But that might be asking too much and might be an overkill for practical applications, right? So yeah, or if you want to be more technical about it, get the L2 norm of, or the L2 relative error of the error vector. So itong L2 relative error, ito ay norm in the L2 sense. Siguro mathematical ko na lang siya isusulat. So meron kang vector W, vector big W, ang laman niya ay yung mga W sub i's. Tapos meron kang vector capital X, na ang laman ay itong mga X sub i's. So you'll get here 11 by 1 vectors. Kunin mo yung difference nila. Tapos kunin mo yung L2 norm. Ang L2 norm ng isang vector ay Euclidean norm lang naman. No? This is the square root of the sum of the errors squared divided by the norm of the vector x that we are approximating. So that's what this L2 relative error represents. So ibig sabihin, in a global scale, yung error niya is about 3.43% with respect to the L2 norm. Okay, I think that's a more mathematical measure of error compared to the average relative error. Okay? Though equivalent lang naman sila kasi finite dimensional lang naman to. Sa finite dimensions, equivalent lang naman lahat ng norms. Okay? All right. And then this table, actually, kaya siguro hindi na-appreciate ng mga estudyante itong solutions na to kasi table lang yung nakikita. Ano? Usually, it's better to express your solution in terms of graphs. A picture paints 1,000 words. So kailangan pwede tayo mag-insert ng mga pictures. So what I did here is to plot the actual solution against the interpolated solution or the interpolated approximate. So yung kulay yellow, siya yung true solution, which I got by solving the problem by hand. Okay? Tapos yung approximate solution natin na binigay ng Eulers method, actually ay yung mga dots. Understandably, sa t sub 0, which is our first discretization point, eksakto. Magi-intersect lagi yung function ay yung true solution at saka yung estimate. Kasi ginamit natin yung initial condition para doon. So there should be no error here at the left endpoint. And then ang susunod kong estimate yung 0.5, function value kay 1 yung susunod, 1.5, and so on. So nakukuha lang natin instead of a continuous function, we're getting a bunch of points. And that's what the blue circles represent. Now, you can use, if you want to get an approximate function, kung hindi ka satisfied na points lang yung nakukuha mo, pwede kang mag-curve fitting doon sa mga data points and then connect the dots. You can use, I think, na-encounter nyo ba yung interpolation? You can interpolate, I think that's what I did here, or what MATLAB automatically did. Kinuha niya yung function, yung polynomial function na magpa-pass through dun sa lahat ng mga data points na nandyan. At yun yung nakikita nyo as the red curve. That's what I call the interpolated plot, which is not what my computer gave me. That's not what Euler's method gave us, because Euler just gave us the discrete set of data points, which are estimates for the x of t sub i's, or x of t sub i's, right? Para lang ma-compare, gaano kaganda yung estimate, kinuha ko lang yung polynomial na magpa-pass through sa lahat ng points na yon, and I compare it with the true solution. And you see that there is a little gap between the two. Yun yung nire-represent ng error. But we already have a sense of how big the error is. We know that the error is around 3.43% nga ba, yung L2 relative error. Okay? I saw Ben Paul raising his hand kanina. Ben Paul?
Sir, based lang sa sinabi nyo, kumuha kayo ng polynomial na nagpa-pass through sa lahat ng points. Isang polynomial lang yan, sir. Hindi siya parang putol-putol na polynomial.
I'm not sure kung ano yung ginawa ni MATLAB, pero I know si MATLAB ang default niya ay isang polynomial lang yung ginagamit niya.
Okay, sir. Kasi pero parang straight yung 0 to 0.5 plus 0.5 to 1 parang straight din. So iniisip ko baka kumuha lang siya ng linear interpolation per 2 points per pair. Pero feeling ko lang yan.
Yeah, that's also possible. Kasi baka ang ginawa niya ay piecewise linear interpolant. Pero, yeah, I'm not sure kung anong internal routine ni MATLAB. Hindi ko to in-interpolate kasi I just let MATLAB draw the graph for me. So binigay ko lang sa kanya yung points. Ginamit ko yung command na plot. Yung command na plot, siya yung naghahanap ng best fit. Be it a piecewise linear interpolant, but I doubt na piecewise linear interpolant yung ginamit niya. Though dito na mag-appear nga na parang parang hindi siya differentiable dito. Which I don't want to happen because we are assuming that x prime exists. So dapat walang sudden turns. So kung i-avoid nyo talaga. Kung kayo manually yung mag-interpolate, huwag kayong gagamit ng piecewise linear interpolants o pinagdikit-dikit na line segments kasi posibleng hindi siya maging differentiable dun sa mga joints. Pwede kayong gumamit ng splines o kaya quadratic splines or cubic splines kung ayaw nyo ng masyadong malaki yung degree ng polynomial. Kasi may isa pang problema kapag malaki yung degree ng polynomial, no? You might be susceptible to what we call the Runge phenomenon. Pero that's more of interpolation theory, all right? But even though I said interpolated plot, I let MATLAB decide what type of interpolation to do, All right? Siguro better to say hindi interpolating polynomial. There's an interpolating function na ginamit si MATLAB para ma-draw itong graph na to. And yeah, so what we'll do is next meeting, dahil overtime na ako ng 6 minutes, what we'll do in the next meeting is to take a deep dive into the convergence and the error analysis of Euler's method. Kasi ang kagandahan kay Euler's method, napakasimple pa niya. Kasi ang bilis ng derivation niya, no? So ang daling i-trace kung ano yung error. So we might have an idea of what is the worst case scenario. We can find an error bound for the error in Euler's formula. Okay, or using Euler's method. And then we will see that if you are not content with the accuracy and the convergence offered by Euler's method, we can do some more work, all right, para ma-improve yung ating estimate. And that's what Taylor methods do. Sila yung natural improvement ng Euler's method. Kaya lang may drawback kasi yung Taylor's method. Yung Taylor's method, kailangan mo ng mga total derivatives. Makikita natin next time kung bakit kailangan ko ng total derivatives pag Euler's method. Alright? At ang hirap mag-compute ng total derivatives, lalo na kung maraming or higher order total derivatives yung kailangan mong i-compute. Alright? So, kaya merong Runge-Kutta methods. Yung Runge-Kutta methods, siya naman yung sagot doon sa mga reklamo na pwede nating mabuo mula dun sa Taylor's method. And that would be for next meeting. Yun yung gagawin natin for the first half of the course. All right? So I'll stop here unless you have some burning questions that you want answered before we part ways. Kasi Thursday na nga pala ngayon, no? Questions? All right. So if there are none, so thank you guys for joining me today. Hopefully by next meeting, we will be doing it in a faster pace. Pero ano pala, no, kalahating oras tayo nag-introduction. So that's fine. So that's it for now. Thank you for joining me, guys. Enjoy the weekend. Let's see each other again on Tuesday. All right. Bye.
Thank you, sir.
Thank you, sir. Bye-bye.
Bye-bye. Bye-bye.